Yeah, thank you very much, Mats. My name is
Thank you.
Laurie. I'm a
Mm.
second year PhD student now at the Raspberry Pi Computing Education Research Centre here in Cambridge, and I'm supervised by Dr. Sue Sentence, who's here. And I can begin now if you're ready, Mats. I'll start sharing my screen.
Yeah, let's do that. Hopefully I get, um, I don't have the connection, so I don't get the sound well.
Can everyone see my screen, including you, Mats?
Well, yeah, we can see it. That's,
Okay, cool.
yeah, it's the sound that we are working on, but it goes with my computer now, so it's workable.
Okay.
No, I don't think so. But that doesn't, I don't,
But just to get the feeling that to be talking to someone, as you were saying before.
yeah, it doesn't show up. So,
Yeah.
so anyway, uh, let's go and we'll see. Hopefully, we will be able to let you see us as well eventually.
Yeah, sure. If you need to stop as well, or like
Mm.
um I don't know, test out some sounds, just let me know. That's absolutely fine. But yes, thank you very much for coming, everyone. It's really nice to be here presenting my research, and it's nice to see some familiar faces too. Um, I've just introduced myself, and my PhD research is what I'm going to be talking about today, which is looking at ways of improving the teaching and learning of debugging for secondary school students. And so hopefully you guys will learn something, or this will be of some use to your research, or at least of interest. So I'm going to start by giving like a very broad overview of why I think debugging in secondary schools is important, and then I'll go through three pieces of work I've done to try and learn more about the problem space, I guess. So as many of us will know from learning to program or even just being a seasoned programmer means getting errors. And these may be fairly simple errors, or they may be ones that are more complex. And sometimes they come with a big, scary red error message, and sometimes they come with a massive stack trace, which is very hard to decipher. Um, but regardless, it's an unavoidable part of learning to program and can be both a common source of conceptual difficulty for students, but also a source of emotional satisfaction when students solve errors, but also a sense of emotional aggravation if they can't. So errors are common and unavoidable for learning to program for any novice. And I think there's additional, or at least different challenges for K-12 learners debugging. And my research is focused on K-12 learners learning a text-based programming language. So the national curriculum for England, and I know this is the case for other countries too, for computing, states that learners have to learn a text-based programming language. So here in England, we have tens of thousands of students who are 11 to 14 years old each year learning Python, which is really good. But it also, because it's a text-based language compared to block-based languages, um, there's like a huge, there's a much less scaffolding and hence a much larger scope for getting errors. Indeed, as we know, in most block-based programming languages, it's not even possible to get syntax errors. And as well as that, the context to just university settings where computing education research is most common is different. There's different challenges. Teachers have much less time per week to teach programming. Often teachers aren't specialist computing teachers or experts. And as well as that, compared to at least most undergraduate courses where students elect to do CS1, students don't get a choice. They can't opt in, nor can they opt out if they're not enjoying the process of debugging or programming more generally. So that's a basic overview, but I think we can like split the challenges of learning to debug for K-12 learners learning Python or another text-based programming language into these three areas, into the cognitive challenges, the affective, emotional challenges of struggling to debug, and from the teacher's perspective, the practical challenges. And so I have three areas of my research which I'd like to talk about. You can treat each of these as mini talks. So if you lose track of one, there's more research to talk about on my side. So let's start off with debugging behaviors of K-12 students. And let's delve into why debugging is cognitively challenging for these learners a little bit more. I didn't really speak about that. I think most of us can accept that learning to program is hard and there is lots to store in our working memory, to use the idea of cognitive load theory. And I'm citing here the original paper where cognitive load theory is proposed by John Sweller, and he talks about when there is lots to store in your limited working memory, you make mistakes, you make errors. And that's what happens when we're learning to program, because we have the program syntax to think about, we have how constructs relate to each other, how a program executes sequentially. We have all of these things to consider, and we will likely get errors. And these errors, if we have limited working memory, are hard to debug in and of themselves, and they may themselves be made based on misconceptions. So if we're developing or if we're debugging something and we feel like we've implemented something correctly because we have a misunderstanding of a programming construct, that becomes hard to debug. Also, as I alluded to earlier, error messages can be cryptic for younger learners, containing keywords that students don't really understand. And you could argue it doesn't really help them in red either, because it implies the student has done something wrong to get to where they are, whereas error messages are completely normal. So all of these things kind of culminate in often novice programmers using ineffective debugging strategies, ones that don't really help them resolve the errors in question or get to a correct program state. And what the computing education literature in this field suggests is that we have like lots of undergraduate debugging behavior studies with CS1 or CS2 students in Java who have learned other programming languages before potentially. And there are some studies that have looked at K-12 learners debugging in something like Scratch, which is great. But as I mentioned earlier, there's much less scope for errors. So the nature of your errors you are debugging is different. There don't seem to be many studies of K-12 students debugging a text-based programming language, despite the fact in England and other countries, like I mentioned, there'll be lots of students right now learning to program in Python. So this is where my first line of work comes in. I wanted to investigate how lower secondary school students go about debugging in a text-based language. So let's look at briefly how I investigated that and then what I found. So this is a study I conducted last year. I recruited 75 Key Stage 3 students, so it's just 12 to 14-year-olds from two schools. These students had spent a few weeks to a term learning Python, so they were slightly familiar. It wasn't like their first lesson, but they were still novices. And then students did this study in a single lesson um, with their teacher. I wasn't in the room. And the first part of it was a set of debugging exercises. And I'll just show you these in a little bit more detail. So students were guided to a website which contained 5 debugging exercises. Each of them had a little exercise description, what the program's meant to do, how many errors it has, and then there's this code editor which contains a program I wrote, and I sabotaged the programs with common errors that novices get. And so this program contains 4 errors. Um, I realize the text is a little bit small, but maybe the eagle-eyed among you will be able to spot where the 4 errors are. And they're on these highlighted lines. So this equals here on line 6 should be a double equals, that's a syntax error. And then according to the exercise description, the or should be an and, the inequality should be a greater than or equal to, and then line 10 should not be indented. And students then were just told, go and debug these programs, press run when you need to. Here's like the console outputting what's wrong with the program or what it outputs. And then every time a student pressed run, we logged the state of the student's program and the time in which they ran it and the exercise they're attempting. And if the student's program didn't run, we logged the error message. So we generated all of this log data, and to be specific, we generated, or students generated rather, like 7,000 snapshots. So that's 7,000 times students are clicking run spread across like 350 exercises students had a go at. So that was a lot of log data. And there are some like learning analytics studies we looked to for inspiration of how to analyze this. We decided to analyze it mostly qualitatively. And this is how we went about qualitatively analyzing log data. So first of all, we made a little tool which allowed us to load up a student's attempt to an exercise, as you can see here. And this gave us information about the state of a student's code, a specific run, how long they'd spent on the exercise, the error messages they were getting when they ran it. And we used this to manually inspect the log data. So this like partially made sense of what students were doing. It showed their thinking processes, or at least showed their debugging processes. And then we looked at the changes they made between runs, and we could do this looking at the diffs between runs. And this allowed us to kind of induce common behaviors that we saw among students. So first of all, generated, as per qualitative content analysis, very descriptive open codes, and then merged these to axial codes and then categories representing common behavior. And so we then had a categorization of debugging behavior, which I'll briefly talk through. But first of all, it's very important to remember that I wrote these programs, not the students. And so the way students debug foreign code they haven't written, will be different to their own because they're not aware of the program as a functional whole because they haven't written it. They'd never used the website or the code editor before. Perhaps that may have taken some getting used to. And the categorization was binary. So what I mean by that is that for each subcategory in the categorization, a student either exhibited a behavior or not. We didn't count how many times a student exhibited the same behavior. We thought that would just get too complex and hard to actually analyze reliably. So then we induced 6 main themes from students debugging behavior. I'll briefly introduce them and then talk through some examples. The first one is the first change a student makes in relation to the exercise. So does a student run their program before making changes, i.e. supposedly looking to the error message for advice, or do they make changes? Are they confident before running code? We saw a lot of students introducing additional errors in an attempt to resolve errors, and this often came from what you might think of as slips of the hand. So students may have been trying to solve a syntax error, for example, changing an equals to a double equals, but in doing so, adding additional syntax errors or other types of errors. Of course, students resolved some of the errors. Unfortunately, this wasn't as common as introducing additional errors. And then some changes students made were we call inconsequential. They didn't really affect the state of the program. So this may include like adding brackets to a condition in if statement or changing quotations in a print statement from double quotes to single quotes. They don't change the state of the program. They don't add or remove errors, but they're changed nonetheless. And then we saw some students supposedly look to the error message for guidance, and some students again supposedly tested their code. It's really hard to tell just from log data. We can't really tell what students were thinking or intending at least, but we can see what their actions imply. And then we had some changes that didn't fit into the above categories, which we'll talk about. But most of the behavior we see is in these emboldened themes. So let's actually look at some student logs, which has been one of the funnest parts of the PhD. So here's 2 students. And what I should have mentioned earlier is after students completed the debugging exercises, they did a little survey about how they felt they did and also their attitudes and emotions to debugging. So we have a female student called Alicia here. She rated her performance 3 out of 5, which is the average or the modal response for students. And she claimed to have ran the code to see what was wrong, basically. kind of implying that she was looking to the error message for guidance. And then we have Gabrielle, who was a bit more confident, and he expresses some general inspection of the code as well as using the error message. And we're going to look at the attempts to exercise 3, as you saw earlier, but just for a little bit of extra context, this program checks if a student should apply to become a computing teacher by inputting their age and if they're passionate about teaching computing. If the user is 21 or over and enters yes to having a passion for teaching computing, then lo and behold, the program will output that their check was successful and they should apply to become a teacher. Otherwise, it's unsuccessful. And as you can see, originally there was an equals here, and then this or needs to be an and then we're looking at if the age is greater than or equal to 21, not just greater than. And then we need to unindent this print statement. So it outputs regardless of the variable allowed to apply value. So let's actually look at some student behavior. This is Alicia. Alicia struggled on the exercises. And before we even look at any of the logs, hopefully you guys can see this. She spent 12 minutes, 40 seconds on the exercise. So almost 13 minutes, quite a long time, and ran her program 32 times. And her first run from when the exercise was displayed on her screen was after 22 seconds. So not too long. And that first run, if we compare the diffs with the original state of the program, is unchanged. So after 22 seconds, she hasn't changed anything. She's just pressed run. And you could argue that's maybe not enough time spent comprehending the program as a whole. I don't think it's enough time to at least understand what the program's doing and read the exercise description as well to understand what it should be doing. But let's continue. If we look at her second run, Alicia makes a very subtle change, which you may have noticed. She adds a colon on the line that the error message is pointing to. And so this implies she's using the error message for guidance, but I classified this as adding an additional syntax error because the if statement already has a colon. If she changes this equals to be a double equals and run the program again, she'll get the same error message. But instead of looking at kind of individual changes between behaviors, you can see that she's just, as well as like adding a colon, she's entered a bit of white space, she's reverted some changes, and she's making a lot of small experimental changes to the line that the error message is pointing to, line 6. And these indeed may be a bit hard to see, I acknowledge that. But as well as that, she's changed the original input statement to a print in an input. This is a kind of inconsequential change, doesn't really change anything. Oops, sorry about that. Let's go back. And then she realizes that this inequality is wrong, but unfortunately she puts the equals in just the wrong place and she doesn't ever resolve this error. So there's this theme of like making changes of incorrect syntax and not being able to really revert them or correct them. Let's keep looking at what Alicia does. So as we can see, Alicia's making very small changes still on these runs, in these following runs. Again, adding a colon, now separating the if statement from the condition. So line 8 doesn't make any sense. And then you may have noticed this is like a very small or hard to detect behavior manually, but it was very, very prevalent. If we look at the time between the runs here and the fact that the program is remaining the same, we see that between runs 19 to 21, Alicia's not really doing anything apart from what I call spamming run. She's repeatedly running the program, but not making any changes. And she's running it really, really quickly. This was something we saw a lot and may indicate some emotional distress or frustration or just emotional detachment with the exercises. Then she adds some plain English. This makes no sense in Python. she says if age equals 21 is met. And so we see this kind of overall strategy of tinkering. This is what I'm trying to get across from Alicia's logs. She makes a small change. She might undo that change. She makes another small change. And sometimes she repeatedly runs the program. So it's this repetitive small change cycle, trial and error, you may call it. And the trouble with this is that lots of the changes she's making aren't even correct. They add additional errors. So Alicia ends the exercise with a comma which isn't necessary in the if statement, um, as well as all the errors that are originally in the exercise. So there are lots of things to look there. Maybe that was a little bit confusing, but that was a common student struggle to a debugging exercise and ineffective behaviors. If we look at Gabrielle, he spent 12 minutes less on the debugging exercise than Alicia, but within 28 seconds in his first run, he got the code running, which is very good. He knew to change the equals sign to a double equals. So great. He's already got the program running, which Alicia couldn't do in 14 minutes. So we can see here. And then Gabrielle makes kind of small incremental changes which help to improve the logical correctness of the program. So first, he adds a print statement to make sure the result the check is printed both times. That's good. May have been better to unindent line 11, but that's fine. He then removes it and adds it again. He then changes the or to an and. Maybe this is informed by testing. We can't really tell from the logs. And then notably, Gabrielle, excuse me, makes an incorrect syntactical change around here, but he's able to resolve it straight away compared to Alicia, who made the same change and wasn't able to, as we can see here. And then Gabrielle's program is in a logically and syntactically correct state after 2.5 minutes. So he seems to be a confident programmer and indeed a confident debugger. He's ended the program in a correct state. So um, hopefully that made a little bit of sense, but just to summarize their behaviors, bearing in mind that these are representations of students who successfully debugged and unsuccessfully debugged. Both run the code fairly early on, but Gabrielle made a corrective change. Alicia didn't before doing so. It looks like Alicia used the error message for guidance, but struggled. Gabrielle didn't really have any error messages. It looked like he maybe tested his code a bit more. And then Alicia made no corrective changes whatsoever, whereas Gabrielle made all the ones he needed to. Alicia instead added syntax errors, and the only time Gabrielle added a syntax error, he removed it straight away, which is great. And so we see this kind of mapping of ineffective debugging behaviors to introducing more errors into the program, and then, of course, successful debugging with removing errors. So what is stopping more students? What is stopping Alicia debugging like Gabrielle? A few ideas. First of all, knowledge of Python syntax, or indeed any programming language syntax that they're using. We saw that Gabrielle was able to correct a syntactically incorrect change he made. Alicia wasn't able to do that. So maybe Alicia could have done with like a cheat sheet or some resources to help understand Python syntax. Also note that Gabrielle got his program running in 30 seconds. That's really positive because if he makes any incorrect changes after that, his program would have gone from running or successfully executing to then running with an error message. Alicia didn't have such feedback, and so her unsuccessful changes accumulated a bit more. Perhaps Gabrielle enjoys programming more or is just more confident debugging. As well, the fact that Alicia had a negative start or an unsuccessful start to the exercises may have made her feel a bit emotionally distressed. But ultimately, we think that all of this points to the idea of fragile knowledge among students who are, again, learning to program, but also learning to debug at the same time. Knowledge that may be partial or knowledge that students may have but can't apply it at correct times or misuse knowledge that they have. Um, I think this is a good idea to view the results through. I imagine some of you will be familiar with this kind of theoretical lens, but Fortunately, don't have time to talk about it anymore. But it's important for research to inform practice. How can these findings do so? Well, we found that lots of students struggled with the debugging exercises, despite the fact that they tended to rate their performance okay and that teachers thought the exercises were pitched at a good level. So perhaps more useful error messages would be good that actually explained or asked questions and avoided super technical jargon for 11-year-olds. As well, maybe some tooling to reduce the amount of syntax error students could get. So some of you may have heard of the idea of frame-based editing or tools like Stripe or Stride. So if you have like a block-based editor, but with text-based programming, that would reduce the scope for some syntax errors, which at least when you're learning to program may be really, really useful. And then also teaching effective debugging strategies, teaching students to reflect and maybe self-regulate a bit before they start the debugging process. Otherwise, they might go on this tinkering process, which is really ineffective, and we want to discourage that. So that was part one. Any questions so far? No? Cool. I'll keep going. And if you have any questions, oh, go ahead, Daniel.
Yeah, so there you can hear me, right?
Yes.
Okay, great. So there was I posted a question in the chat,
Oh,
and we
sorry, I
had
didn't
some
see that.
discussion about it. No, that's fine. So the question was, could you see the inputs from the runs? Because technically, I mean, for Alyssa's code, I mean the errors that stopped execution, they were after the input statements. So she could run it and try different inputs. It wouldn't help, but at least you could see if she tried different inputs to see if she gets the same errors for different for different inputs. So maybe she was playing around with the inputting different ages to see if that actually affects the error that she would get.
Yeah,
But
that's
do
a
you
great
have that
question.
data so you could see the inputs during the runs or?
Fortunately, we didn't. We
Ah,
decided not to track that because we thought that students might enter personally identifiable information, but on reflection, it's something we should have and then sanitized if they did. But you're right, and it makes it harder to conclude how students were testing or if they were even testing. Um, but yeah, every time you see it execution interrupted error message, it means the program's run a little bit, but they've just cancelled execution. But yes, if I was to do the study again, I would definitely track that stuff, Daniel. I think it's really useful. Okay, let's move on. And if you have any other questions, please just like interrupt me. I might not see a raised hand, but I'm more than happy for you to ask. So, as we saw, some of Alicia's behavior may have been ineffective, but also if you imagine yourself spending 13 minutes on an exercise and not being able to get the program really running or doing what it's supposed to, I imagine you would feel frustrated. In fact, on Tuesday, I was debugging an error in my code, and I said to my office mate, I'm going to quit my PhD if it didn't work in the next run. That's emotional distress, and I've been programming for a little while. And it's the same in novice programmers. So students in undergraduate studies have reported, or at least teachers have reported students feeling at a complete loss. Some students report this struck by lightning experience when they run their code and it gets an error they weren't expecting. And we see all of these negative emotions. Some students look horrified when they get red text error message. Um, Even some students might have had such bad experiences with debugging that they just expect their code not to run when they press run. So that's really, really not good. And of course, solving an error can be really satisfying. And I'm not saying students never do that, but I'm saying it's quite an emotionally polarizing process because if you solve an error, you feel absolutely amazing. You don't just feel okay. But then if you don't solve an error, you feel all of these emotions that we've just looked at. And so debugging is emotional in nature, especially when learning to program. As we've seen, it can lead to frustration, maybe embarrassment as well, if you think that getting an error reflects your programming ability. One of the studies here, which I'll circulate with the slides, reports like a physical reaction to getting an error. So these things are powerful. And also, if students fail to debug successfully and have negative emotional experiences, they're likely to develop negative attitudes towards computing or maybe just programming or debugging. I've been visiting some schools as part of my research, and one student in a classroom was struggling to troubleshoot one of their programs. And I was just walking around. I didn't even say anything to them. And they just said when their program didn't run, they said, I hate computing. And I asked them, why is that? That's a very strong word. And they said, because I can't do any of it. And so while this doesn't point to the emotional distress, it does point to the fact that a lack of successful initial experiences does develop negative attitudes. And we certainly don't want students to hate computing. And all of the studies I cited looked at kind of emotions when programming generally, and they all seem to arise this theme of like the emotional journey of bug fixing while not focusing on debugging specifically. And again, lots of these studies are at an undergraduate level, sorry. So I wanted to look at lower secondary schools students' thoughts and feelings towards debugging. And that would link nicely with the log data I saw or observed to see if there was a relation between these two things. So after doing the debugging exercises in the study I explained earlier, students then completed a little survey. It was a very short one. They had just had a go at some exercises which they may have found hard. But first of all, they rated their performance on the exercises on a scale of 1 to 5. They then answered some free text questions. Most notably, we asked them what debugging techniques they used for the exercises. And then we wanted to investigate some attitudes and emotions that we found common in the debugging education literature. And so for each of these attitudes and emotions, we had 2 statements related to them, which were responded to on a 5-point Likert scale. And then students just entered their school year group and gender. And we looked at the main thing we looked at was the correlation between these attitudes to investigate how they relate to each other. So I'll report them now. And we use Spearman's rank for the correlation. So it gives a value between -1 and 1. The closer the absolute value to 1, the stronger the correlation. And we only report statistically significant correlations here. But the strongest of them was between students' self-efficacy, how confident they believe they are in successfully completing a task, and how well they feel they performed in the exercises. Perhaps not too surprising. But then some of the other correlations I think are really interesting and important to note. So there was a correlation with a strong effect size between reported feelings of anxiety and frustration. And while most students didn't report feeling anxious or frustrating when debugging, of course, some did. And those that reported feeling anxious also reported feeling frustrated and also reported lower levels of self-efficacy. Interestingly, girls reported statistically significant lower levels of self-efficacy related to debugging, as we've sadly seen with kind of programming and use of computer self-efficacy as well. And there were some correlations with usefulness. And now I don't think that well, I think some particular correlations are important, but what I think this shows is the role of self-efficacy, right? Like this is not causing the other attitudes, but it's at least associated. And we know, or we propose from self-efficacy theory that the initial success of the student has in a task, as well as verbal persuasion and the emotional arousal they feel, contributes to their confidence. So if students are feeling anxious and frustrated when debugging, of course, they're likely to develop a negative self-efficacy. We also looked at what students' reported debugging behaviors were. And this was really interesting to kind of triangulate with the log data which looked at. And this was the question. The common answers were just running the code to see where the errors were, which we saw a lot. I can't remember off the top of my head, but I think the median time to initially run the programs was somewhere between 10 and 20 seconds, like we saw with Alicia. Some students mentioned repeatedly running the code. Many students spammed run, and in fact, that made up almost like half of the runs we saw in our log data. Some students mentioned more deliberate inspection or comprehending of the code, perhaps where a bug is more likely. And then some students also mentioned using external resources. I think it's great students search the internet for debugging advice. I do the same. And then some students mentioned this ineffective strategy of trial and error, or as I call tinkering, which we've seen. So I've gone through that fairly quickly, but what does this all mean for lower secondary school learners and teaching programming and debugging to these students? Well, like I said, debugging is emotional, and I think every teacher must consider the attitudes and the emotions that can come from negative or even positive experiences when solving errors, which we know are often difficult for novices to do. We saw the prominent role of self-efficacy, and while that may not cause other negative attitudes, it is related to them, which is important to note. And we saw some mention of ineffective debugging behaviors, which we observed in the log data too. And similar to the recommendations from the debugging behavior part of the talk, we think effective debugging behaviors should be explicitly taught to students. Okay. Part 3, the teacher perspective. Any other questions so far? I can see there's 15 messages in the chat I haven't read.
Okay, I have some comments. Can you hear me?
Yes, I can.
Yeah, so this is close to what I've done and what we plan to do in a research project.
Mm-hmm.
And we found that positive emotions were connecting to coding yourself, and positive emotions were connected to better long-term memory. And the hypothesis we have is actually that positive emotions that can come from programming, because this can be like a roller coaster, can actually influence short-term memory in a good way, because the short-term memory is kind of a bottleneck for learning. Our short-term memory has a really little, our short-term memory is very limited. And positive emotions can ease the pressure on working memory. This is our a hypothesis, and it can go through bodily emotions. I mean, you do this. And easing the load on working memory means that it has a bigger chance to go to long-term memory, which means that you have learned, so to speak. And these were upper secondary school students. So I think very much what you say applies to upper secondary and I think to university students as well. So we recognize it at all levels.
Yeah.
So and we have so I don't we met in Cooley. Do you remember that, Cooley College?
Yeah.
Yeah. I don't know if I send you a paper we had there some years ago. Christina von Hauswolf was the first author.
Okay.
Maybe I sent that paper to you.
Not sure. I didn't think you did, but I'd be really interested to read it.
Yeah, we have this strong connection between self-efficacy and learning, as you have.
Yeah. But then you mentioned as well a positive effect on learning with coding yourself, right? So it's important students are debugging maybe their own programs, do you think, rather than others?
Yeah, that had to do, we call it motoric actions. That you do it yourself in some way is important. Yeah. So I don't know if how this has to do with others or your own program. I don't know.
Yeah, no, I think that's a good point. it's harder to control the difficulty of the errors that students will get if they write the program themselves, though, and therefore it's harder to control the, like I keep saying, the like initial success they get when debugging.
Yeah.
And so it's a hard challenge. But
But
I think
I can tell you what we plan if we get funding. We plan to look deeper into emotions. We plan to use this huge instrument from Peckrun. You've probably heard of this researcher who has done a lot of emotional research. But that's self-reporting on,
yeah.
And then we want to combine it with one of these, bracelet that you have, and you measure physiological reactions in the body, sweating and heart rate and blah, 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 blah. And if we can combine these two things, we believe we will have a stronger data to understand what happens really. So this is what we plan to do.
That sounds super exciting, Anna. I'd love to hear about it. And
yes, and I'd love to get the funding.
yes, yeah, I really hope you do.
Surprisingly.
Well, yeah, thank you very much for that. That's a good point. Definitely one for me to dwell on with Sue. But I'll move on to the final bit. This isn't very long because this is still in progress, but I've talked a lot about students' perspectives of debugging. Teachers in lower secondary school students or upper secondary school or even lecturers have challenges to do with debugging. So let's look at the practical challenges. So at least in England, through interacting with teachers, we see this quite prevalent problem that there aren't enough qualified computing teachers. And as a computer science graduate, I look at where my mates have gone. They've all gone to very well paid jobs in industry, which are less stressful than teaching and pay more. And that's maybe one of the reasons for this. But at least in England, what we get is a lower secondary school level where all students have to learn computing, maths teachers or business teachers who have only recently learned to program, teaching Python. And so that is, I think, extremely noble of them and like really, really good they step in, but also since they're not experts in the language, they may not be as best equipped to help compared to someone who's been programming for years. And in addition to that, through a study of Tillman McKaylee, but also personal observations, programming lessons at 11 or 12-year-old level can be quite chaotic. And when students do get errors, they often straight away just put their hand up. And of course, if every student or many students put their hands up when debugging, teachers can't really serve every student effectively and they report rushing around the classroom. So even their emotions during the lesson are affected. They may feel like rushed or maybe a little bit anxious. And also, programming is typically taught for, at least in England again, 1 hour a week compared to an undergraduate level where students spend more time learning the basics of programming. And even though computing is taught 1 hour a week, sorry, programming only makes about 20 to 40% of teaching time. So students learn to program for a few terms a year. They don't spend that much time doing it. So this makes it very hard for teachers to teach both programming and hence solve errors. And again, there doesn't seem to be lots of literature investigating the role debugging plays in teachers' experiences. So we wanted to investigate this and kind of their perspectives of teaching debugging, because some teachers are very, very confident and have great ways of scaffolding the process of bug fixing. So like I said, this is in progress, but what we did to achieve this is we just interviewed 10 lower secondary school teachers who had taught computing at a Key Stage 3 level. And then we asked them a few questions. First of all, based on some of the things we saw in students. So we asked them about common errors they saw, common emotional reactions they saw in students, and also common debugging strategies they saw to, again, kind of triangulate this with data we'd collected from students to get an idea of what's actually going on in the classroom. We then wanted to ask teachers about how they would support students who are struggling to resolve an error. And of course, it was important to ask them like what research would be beneficial for them, because we want our research to inform practice and help teachers. So we thought this was important to ask too. And so I'm still analyzing this data, so I report this in quotation marks, I guess, under construction. But some teachers seem very, very confident teaching or helping students with debugging. And some of these teachers we interviewed were teachers of private schools or had been teaching for years and years. But we can see one of these teachers says they don't even get that many syntax errors, which is completely different to what I saw in my log data, where students were on average in a syntax error state for about a minute per attempted exercise. And on top of that, a teacher mentioned that even when students do get syntax errors, they're not that frustrated. Again, contradictory and therefore interesting, and I look forward to investigating it more. Some teachers have taught this heuristic because of the bad error messages in Python that if you see an error message pointing to a particular line, look at the one above. Students seem to get on okay with that. And one teacher, I just thought this was so amazing, got their students in year eights, so 12-year-olds, learning how to use the debugger. And so they were debugging by themselves, stepping through their own programs. I think I first did this when I was 19, and there are 12-year-olds doing it. It's amazing. But that is contrary to the ineffective debugging strategies we saw. And then we got some additional kind of information because we asked students to report their emotional reactions, but only on a Likert scale. Teachers mentioned some negative physical reactions like frustration or shouting, but also this like real sense of pride and satisfaction and like a physical raised fist in the air when solving errors. Again, this emotional polarity we've spoken about. And the last two questions we asked students were to do with how research can help with debugging. Teachers talked about how it was hard to cater for every student, both in terms of the diversity of ability, but also just like going round to every student is hard and almost an impossible task. Some students don't stay motivated when they solve errors, they just stop. Helping those students is really important. And so teachers suggested like a concrete, explicit debugging strategy, of which there are already some in the literature, which we'll talk about in a little bit, or also some debugging resources. Some mentioned like a trajectory of exercises that tackled common errors that students will get. And these are all things that perhaps my PhD contribution could help with. But just on reflection, before we have some time for some discussion and questions, what did we learn from all of this research so far? Well, at least in the data I've observed, students, when they are struggling to debug, display ineffective debugging behaviors. In particular, they may repeatedly press the run button, they may tinker with their program and get it into such a state that it becomes very hard to successfully resolve every error. It's almost like a slump that they get into, which is very, very difficult to come out of. And so these errors build up and become hard to resolve. As well as that, attitudes and emotions are interlinked to do with debugging. At least that's what students report, and particularly self-efficacy is particularly prominent, I should say there. And from study two, what we've learned so far is that teachers can't go around helping every student with their hand up to debug, or at least can't do it effectively such that students really learn the misunderstandings they have to do with debugging in a teacher-student interaction. As one teacher put very well, a more scalable model is needed. And the teachers that mentioned having some way of dealing with errors were the ones who seemed that their students were more confident, surprisingly. So that is inspiration to make that happen for every teacher. So how could this be done in relation to all of the challenges we've talked about? Useful error messages. I know Brett Becker and Paul Denny have done a bit of work on this, and perhaps there's some role that generative AI could have as well. Tooling to help with syntax errors and to reduce the barrier that they pose to some students. And again, like I mentioned, some specific pedagogy for teaching debugging, which may be generalizable to just any novice programmer, but maybe needs to be particular to lower secondary students as well. In terms of improving effect in students to do with errors, normalizing the fact that errors are just a standard part of programming and that software engineers spend a significant part of their time programming. So students shouldn't be embarrassed or feel bad if they get errors, but instead to remain emotionally composed. And like we've talked about, and I've mentioned a few times, giving students opportunities to actually debug successfully to begin with. And then, as teachers mentioned, having specific pedagogy, but also specific debugging exercises or things like that would be useful. And so the plan for the rest of the PhD is to focus on one of these, I guess, points to help improve the teaching and learning of debugging for secondary students. Thanks very much for listening. I hope this has been interesting and you've learned something. Mats, I don't know what we usually do now. I have some discussion questions, but if
but
you'd rather we can.
I rather need some coffee. So could we take like a 10-minute break? And then
Yeah,
you
of
could
course.
maybe post your questions if you have them written so people could be thinking about them while I'm having some.
Yeah. I just went here they are. Oops.
I'll make a pause in the recording and then see you in, well, 20 past then.
Okay, sounds good.
Many comments.
How to stop a conversation. But Larry, did you have some things that you especially wanted to bring up?
Yeah, I had some questions, so I'll just share my screen again. But if anyone else has any thoughts or ideas, I've seen there's some in the chat, which we can discuss. But I'm aware that some of you are computing educators or like teach CS1 courses. So I was wondering how these findings relate to your experiences of teaching introductory programming or learning to debug, if that's something that you've done recently. And then any ways you found are effective to teach debugging as well. If you think it's better to have pedagogical or technical solutions. And then the token question at the end, how could generative AI help with the teaching and learning of debugging? And we can generalize this. This doesn't have to just be for secondary students. It can be for anyone learning to program in a text-based language.
I have a question. If maybe somebody can answer this. Let's say that I have a physics exercise or a mathematical exercise where I have a longer problem that I have to solve. And often, okay, like in a textbook, okay, or given by the teacher, you might have the correct answer, but you don't have a set of steps. And when you arrive in, okay, with the wrong answer, okay, like how is that debugging process different, okay, from debugging a program? When, okay, you arrive in the wrong solution, and then you need to like figure out why. And how do they teach that, okay, in maths? Or do they? Do they teach like debugging mathematical proofs and and problem solving?
Maybe I can just try to answer this question. So I am in an engineering education working group, and so we also do mechanics and electrical engineering, and well, we also do interviews with students on how they get to the wrong answers. So yes, there is debugging, and like if like there's a big car and a small car, and the small car is pushing the big car, a lot of students think the big car is exerting a bigger force on the smaller car than the other way around, but that's not true. So there is debugging with physics and mathematics. I think maybe it's not so different. I think the big difference is that, well, programming languages are something that we made up, and physics exists without humans. But apart from that, I think our understanding of it is quite similar. So yeah, I think we maybe could learn if you kind of try to look at what are they doing in physics education and try to apply it in
Yeah,
computing education and the other way around.
Yeah, this came to my mind because my daughter is currently reading for the high school final exams in chemistry tomorrow, and we were calculating a problem we got double the result that we were supposed to have, and now the question is where did the two come from? And it's very similar to like debugging a program, at least to me. Like you start from the end and you try to figure out like where is which two did we like fail to put into the equations. And as far as I know, like students, I don't know how students feel about that kind of debugging, like in comparison to debugging programs. Like I guess it's frustrating as well, but it's frustrating in a different way. Or is it?
I guess additional frustration of debugging in programming rather than troubleshooting in, I don't know, a physics equation that you may have misunderstood is that um, a program is meant to do something a lot of the time, at least. So if you make a change which has no effect on the error message, that's really, really counterintuitive because usually your actions have consequences on your environment. That's not the case sometimes when you're debugging. And you don't really know, I guess, if you have like a solution to a problem on paper, which I'm not sure if that's what you're referring to, Otto, you need someone to tell you it's wrong or right rather than an interpreter or compiler being able to do that. So I guess it's kind of just more, I'm not sure what the word I'd use, kind of tangible, the like sense of not being able to change anything if you're struggling to debug. I'm not sure. And Daniel, you had your hand up for a while.
Yes. Yeah, I would say in general, I would say it's the same thing. I mean, the same kind of skill. So in December, I gave a talk here, and then I talked about how the skill of debugging relates to variation theory and learning. And I mean, Samuel Morton, he has, I mean, he coined this concept ages ago, surface versus deep learning. I mean, understanding stuff. And I mean, the surface learner just memorizes stuff, and the deep learner, I mean, they try to understand what's happening and get an understanding. And he showed that these two types of learning, so for instance, so particularly the deep approach to learning is very tied to variation theory and the patterns of variation that one should use to teach things. And also shown that those students who use the deep approach, I mean, they introduce this patterns of variation for themselves when they are learning things. And it occurred to me that when I do debugging myself, because I mean, I've been programming for many, many years now, and I've debugged a lot, and I do it a lot of the time. And I mean, the way I do debugging is basically introducing these patterns of variation for myself to get myself in a direction to learn about what is wrong in this situation and why does this happen. So I've been thinking about how to connect these two and actually teach so that the students, because I think I haven't done a study yet, I want to do that those students of mine that are naturally good at debugging, they are also the students that naturally go for the deep approach to learning. As opposed to the struggling students are probably those students that also have a more surface approach to learning, and then they try to use that same approach when they are debugging. And of course, that will be super frustrating if you don't have trained this skill. because basically my hypothesis is you need to really be good at this deep approach. Then you're good at debugging. So then it should be super frustrating to be one of the surface learners and then hit the wall of debugging, and you don't have that skill at all. So that's my theory. Want to investigate it at some point.
Yeah, I like that a lot. I haven't read into variation theory, did you say?
Yes, exactly. So
Okay.
Martin has a book, Necessary Conditions of Learning. I can recommend reading that one. It's a nice read.
Okay, nice. Yeah, I guess you could argue that like you can't debug with at least little bit of deep knowledge, or at
Exactly.
least debug intentionally.
I think there is a recording on YouTube as well, so you can see what I said about that topic in detail.
Okay,
I think
cool.
Lennart was
Will do.
after me.
Yeah, go for it.
Hi, thank you, Laurie, for a great presentation and the slides. I love them.
Cheers.
I've been into the teacher's perspective for many years, and I I like your findings where you are finding a contradiction between study 1 and 2. And how will you push forward, and how will you use the contradiction in itself as a tool for make new findings? Or I'm especially interested in the why are the teachers so unaware of the emotional dimension among students? I think that's kind of interesting.
Yeah, really good questions. Thanks, Lennart. Um, like I said in the slides, I'm still analyzing the data, and so it's not just completely contradictory findings. There are some teachers who report, like students struggling with syntax errors and getting emotionally aggravated. But my hypothesis is that the teachers who don't report that are the ones who are very confident, who have been teaching for a long time and have worked out ways of dealing with this, but also ones which contain motivated students. Because a few of the teachers I interviewed in some of those quotes are from teachers of private schools, where students pay a lot of money for their education. But in terms of how I'm going to use the contradictions to inform my study, not something or my contribution, it's not something I've thought about yet. I think I need to look more at the data to get an idea of how much contradiction versus complementary findings there are, if that makes sense. But I also do think, I was chatting to a teacher last week, I do think some teachers think things are plain sailing if their students remain quiet, because we don't know if a student's not giving any visible signs of reacting to errors. We don't really know what they're thinking sometimes, and we don't have time as teachers to walk around every student. So maybe that's a reason they don't know exactly what's going on, because some students remain silent.
Yeah. Yeah. Thank you.
Before we let the next question, I think work from Virginia, for instance, like role modeling, could be quite relevant here in this question you had, Lennart, because in some sense, I think even if a teacher who has a very low confidence, there is still this view of the teacher should know. And I think that might be an explanation for why you see this, because they have this image of, well, I'm the sage of the stage. I'm the one who's actually should be knowing this is my role, not showing that I'm also frustrated. Like in the working group, there were just a few teachers who actually said that this is important to show that this is not just you. And another thing about what you said, Daniel, about this deep and surface learning, I think one thing that might come in here is that in traditional studies, surface learning typically pays off. I mean, you typically pass exams pretty good by surface learning, whereas maybe this programming is very unaccepting to being a surface learner. So maybe that's something that comes in as well. I just thought
That's an excellent point.
True.
And
But
it makes me think of fixed and growth mindset as well. So you mentioned you can have surface learning to pass exams. If you have a fixed mindset, then you're more concerned about passing exams rather than actually mastering the skill. So maybe there's a mapping of like fixed mindset, and we've seen the effect of challenges of debugging to surface learning, and then growth mindset to deep learning.
oh, sorry, I took the spot there, Jesse. You could.
No, not at all.
So, can you hear me?
Mm-hmm.
Okay. Hi, Laurie. Thanks for your great talk. I have some comments,
Sure.
but some smaller ones, which I will send to you through Slack because they're quite specific.
Cool.
I actually want
Thank you.
to come back to Otto's question on the physics and the chemistry one. And something I think is interesting there is what you said as well, is changing a program doesn't necessarily give change in the result of the compiler. Well, for a physics thing, if you change something in your formula, you'll get a different result. And something else I think is in physics and chemistry, we do the problem solving and then we do the computations. And you can make mistakes in the computations. And when there's a mistake, like I have the double or half of it, you sometimes just made a computation mistake and you have to fix it. But a computer doesn't make these mistakes. So the only issues you get in programming is the problem solving ones, which are much harder to figure out than the mistake in computation. So that might also be a reason why it is just so much more frustrating, because it's just a higher level of thinking, a much harder way of reasoning about the problem.
Yeah,
Yeah.
definitely agree with that. Like I said at the start, I think learning to program and hence solving errors puts lots in your working memory. And I think the idea of variation theory could relate to that. So I'm really excited to read about that.
Okay, thanks.
Thanks for that, Jesse. See you again. I'm just looking at one of the chat questions from a little while ago about uh from you, Daniel, saying when she runs it several times, she's likely running with different inputs. I know you asked that in the thing, but only one of the students did that. I think it's worth pointing out. So one of the
Okay.
students, I'll just keep scrolling up. This student, Alicia, um, because there's incorrect syntax, her program never ran at all. So you don't ever see this like execution interrupted error message. And that's why I think
So it doesn't execute at all.
Yeah, exactly. So if you just look, you don't need to look at these things, but if you just look at the error message, syntax errors in Python stop the whole program from executing. That's not the case with runtime or type or like name or value errors. And so that's what I think is so annoying that she spent 13 minutes on an exercise which isn't hers and she hasn't got it working, and then she's moved on. That is the epitome of the opposite of a successful experience. And then I noticed someone in the chat said maybe the exercises were too hard. I think that could be the case, but like I said, we did ask the teachers, so we went through with the teachers the exercises and said what needs changing, and we had to change a few things. And also, I think there's something to be said about the fact that the responses to the how do you feel you performed were normally distributed with the first value being neutral. Maybe students just picked a random option, but the fact that they feel generally they performed okay maybe suggests that the debugging exercises were fine, but that the debugging behavior we saw was representative of what they commonly exhibit. I'm not sure. And even if the exercises were too difficult, maybe it shows something about how they go about debugging things and programming concepts they're not confident with. Any other questions or thoughts? Keep scrolling through the
I
chat.
can continue on that actually. Yeah, so one thing I was thinking about, you said when you constructed this one, I mean, you wrote the program and then you introduced several bugs. So I
Yeah.
was thinking, I mean, if that is representative of how they actually write code. So because I've been working with Johan in the UpCERG group, so he has also looked at a lot of code. I mean, lots of these traces of how the students write and run code, and that they can run it a lot, and they write and then run and write a bit and run, which kind of seems like we haven't looked at the details of what is in there. Or at least I haven't. Johan might have. So it feels like if when they write code naturally, maybe they write and run often, which means then they would get these bugs one after another. So I mean, when they've written something, they try to run it, they get that bug. So it's unusual maybe that they get like 5 bugs at the same time
Yeah, yeah,
between
yeah.
2 runs. And maybe, I mean, that kind of relates to the break discussion that we had about the history, because then if you run often, then kind of you keep the history in your head because you make one change at a time between the runs. So it's a smaller space there to move in for the one who is doing the debugging and writing.
Yeah, I
So
think
that
that's
was
true.
just a thought.
Yeah, I think that's true. And I think some of the teachers I spoke to encourage their students to make small incremental changes. But I think, like I said, the trouble with that, if you're tinkering, is if you make an unsuccessful change, you have to revert it straight after. Otherwise, they build up. And then they might build up to a state where it's so hard to actually get back to the original correct state of the program. And that's maybe also where you need like a rewind button. I'm not sure. But that's why I personally wouldn't. I think making small changes is good, but get your code at least successfully executing first. And it's different because Python's interpreted. Like if in Java you might get 10 different compile errors, and then you are encouraged to solve each of them in turn because they're all appearing at the same time. That won't happen in Python. Otto.
Yeah, I could just like a recap, okay, for the coffee people in Uppsala. So just so what we discussed like during the break was like that was exactly like this what Daniel also mentioned was that this it would be really handy if you could go back to the last known good state and okay then see okay, like what did I change in this case. Okay, let's say the last known good state was if age is equal to 21, then okay, like go to the allowed to apply and whatnot. And okay, and the change was okay that you added okay this or computing degree equals something. And okay, like this last part, like it was working, it was doing okay something correct, but now it isn't. And okay, how useful this would be both for the student and the teacher to see that okay that the students where like which change broke the students' program. Okay, it probably didn't do okay, like it was logically wrong, like the original one already. It didn't do okay exactly what was requested, but okay we could see the change, and that would okay help the TA or the teacher a lot okay when helping the student okay to see okay, like what were the last steps you did after you okay change your program. And this is actually okay, like something that I find like I'm now going to introduce our local LMS as well, so that I could see more easily what are the changes between like students' subsequent submissions to an exercise, like which lines did they change between okay two submissions, because then they come and okay they ask the TS for help. Then okay I could see that okay, like that yeah you got okay 60 points and now you are down to 30. So what did you change? And okay, and these were the things. Okay, then it might be okay a lot easier. So this suggestion okay, of the rebind button would be okay, like that also that you could easily try something and then go back to whatever you were working with. Sometimes it's also really nice, like you could write, I guess, some print statements and And then, okay, you wouldn't need to like go about and delete them. Okay, you would just rewind them. Okay, they would automatically go away. Would also be debugging sometimes like nicer because you could just try out things and then you can like just snap back to whatever you were doing. Yep.
Thanks for the recap.
I think I need to do it pretty quickly now, maybe. I'm thinking that when we speak of this frustration, I think that as Anne was saying that, okay, I do recognize this from my own students, and I noticed that Aletta also nodded, and I do that myself from teaching C# to a big number of students. So basically, they did the same faults as Alessia and Gabriel. However, what they don't really recognize is the frustration. These students, as in university students, they were more like curiosity driven and what is this? And more of a joyous mindset, if you wish. So I'm thinking that if we can increase curiosity among students as well, maybe that could bring another mindset, and they would actually learn more. So that would be a very cool research project, I think, like curiosity-driven debugging among K3 students.
Yeah, no, I think partly, I guess, why do you have programming? I think that's the question here. And if the answer to that is something fun or that provoke your curiosity, then maybe you're in a much better state than when you are kind of forced, I should do the programming and it doesn't work and it's frustrating. And I do think that the emotions here is playing a lot, and the self-efficacy thing you had there is probably quite relevant as well.
Yes.
And we're getting to the end of this, and I just want to make was it 2 weeks ago? We had Leo Porter, or 3 weeks ago. I think that's something where you could, if you look at that recording, you can maybe get some ideas around using the generative AI. And I think what he also talked about kind of addresses this frustration thing, because he was talking about lowering the barrier, kind of making it easier to do things. And that's maybe something to try to use. And I think the other examples you had there about sort of actually making the debugging explicit, making it kind of helping them to get understanding of what is debugging. And I think that would be quite an important thing. But also look at Leo's presentation. I think that there are always connections there. And quite
definitely.
And thank you, Laurie. This was very well presented, and wow.
No, thank you so much for having me. Really, really useful and interesting discussion.
Yeah. Oh, well, we'll keep in contact, I guess. And,
Come and visit us. Come to Uppsala.
Very forward.
Yeah.
We have very good coffee. Of course, not as good as Finland.
Yeah, well, you guys have my email. And Kalkin, I noticed you had your hand up. I'll put my email in the chat if any of you want to have desperate questions you'd like to ask.
Yeah. And this recording will of course appear in the in UpCERG seminar list. And I guess also if you send me the slides, we can put them up as well.
Yeah, of course. They're in the chat too somewhere, I think. Okay. But yeah, I'll email them over.
Yeah. So thank you all, and nice to have seen such a varied audience as well on the Zoom. So yeah.
Yeah, nice to see everyone.
Yeah.
Thank
you, everyone.
Bye.
Bye-bye.
Thanks for the presentation.